Now we're going to look at how we can use inference to interpret regression coefficients. And this is an extension of the same idea that we have done for simple linear regression, when we computed confidence intervals for the slope and/or conducted hypothesis tests about whether or not the slope was zero. So for our multiple linear regression model, here is our general form. We're assuming our true underlying relationship, or our true underlying model, ground truth model here, is linear in our parameters. And then we have some noise here, which leads to random variation in our data. We estimate our best fit theta values using our sample. And so what do we mean now by the slope, right? So when we had done this for a simple linear regression, our model had looked like this, and our slope would have been theta 1 here. Now I want to think about what this means in the context of more than one, just one feature here. And we're going to answer the same types of questions that we did with simple linear regression, like what if the true parameter is 0? Or can we figure out whether it's positive or negative? What does that parameter even mean? And can we infer anything about the true underlying parameter given our estimate? So one thing that we've covered repeatedly is how much our estimate depends on our sample. And so it's possible that the true underlying parameter value is 0. And if that's the case, then this feature, x1, really is not important to keep in our model. So it is useful to try to test whether or not we have some parameters that have shown up in our model just due to random chance and not due to a true association. So this is the idea of what we've used in simple linear regression of when we used hypothesis testing. And we're going to do the same idea here. Our null hypothesis is that the true parameter is 0. The alternative is the true parameter is not 0. And if our p-value is small, we'll be able to reject the null. If we don't want to do this just via hypothesis testing, we can use a confidence interval. So we can compute an approximate 95% confidence interval with bootstrapping. If the interval doesn't contain 0, we can reject the null hypothesis at the 5% level. So this is the same framework we used for simple linear regression. We're just going to extend this idea now for multiple linear regression. So let's do this with an example. Let's pop over to the notebook. So I'm in the modeling folder, the linear regression subfolder, and then in the OLS inference notebook. So let's load in the data. This is the same data you actually used in your assignment on simple linear regression. And we're looking at data about this bird that lives off the coast in California. We have data about the eggs and then the actual weight of the birds that hatch. So we're interested in saying, can we use some of the egg data to predict the weight of the bird when they hatch? And this is useful in the sense of the bigger that a newly hatched chick is, the more likely it is to survive. And so if we can have information about how likely eggs are to survive, this could be useful. We did this already in your simple linear regression assignment, but we only chose one of the predictors, or one of the features, to predict bird weight. So now we're going to use all three and an intercept. So in particular, here's the form of our multiple linear regression model. And again, in this framework of modeling and using models for inference, we are assuming that, yes, this is the underlying form of the model, but then there's some random error, which is unobservable, but we will assume this error here, epsilon, has an expected value of 0 and that their IID, like each data point's error, is independent and identically distributed. So let's fit our OLS model to this, and we're going to print out what we get for our coefficients as well as our RMSE. All right, so there's our intercept. Here's the egg weight, egg length, egg breadth, and then the RMSE. So here again is our underlying model. And here are the coefficients that we found in our notebook. And so a question that we could ask is this the right model? And we could start with, let's test the null hypothesis that the true parameter for the egg weight is 0. So maybe egg weight is not that useful of a predictor of the bird weight. Maybe we see this positive slope here just by random chance because this is a random sample. But maybe we don't actually need this egg weight term in the model. So to test that, we are going to bootstrap a confidence interval. Here's the code that we have here I want you to fill in a couple things. What do we need to do here for the resample? How are we going to do the estimate? So take a minute and think about what you'd put in here and here. And then we're going to pop over to the notebook and fill it in. Okay, so here's the code where we're going to create this function to bootstrap. And we've also created a function just to get the first parameter because that's what we're doing for this particular first question. So to resample, because I have a data frame, the data frame here is called sample df, I can take that and call the sample function. I want to get a new sample of the same size. So n was the length of the original data frame. And then I want to do this with replacement. This is part of my bootstrapping. All right, and then when I go fit the model, I am going to put in my resample x and my resample y as the inputs. And because I am trying to do a 95% confidence interval, I'm going to put 2.5 here for the lower and 97.5 for the upper, and then run it. Oops, I have an extra. There we go. And I need a comma after that one. There we go. Okay, so now let's run it. I'll pause it because it takes a little bit of time. And we find something interesting. We find that our 95% confidence interval does include 0, which from our statistical standpoint means we fail to reject the null that this parameter is really 0, that this theta 1 is really 0. In which case, if it was really 0, let's go back to what it was. That's our egg weight. It's saying that this egg weight is not a useful feature to include in the model. But before we make that conclusion, I want us to think about this a little further. I want us to actually look at the other coefficients before we get too hasty in throwing out that first one. So I'm just updating the code above, but now we're going to get all parameters out. And we're going to do the same idea. Here's my simple resample. Here's my bootstrap. And I'm going to make confidence intervals for all of the model coefficients. So let's run this here. It takes a little bit of time. And here's what we get. And this is even stranger because now all of these, this is a 95% confidence interval for the egg weight, 95% confidence interval for the egg length, 95% confidence interval for the egg breadth. All three of those contain 0, which prevents us from concluding that any of these three variables is significantly related to the response. But this feels very fishy because, of course, the weight and length and breadth of an egg is going to be related to the weight of the actual bird that hatches. So what is going on here? So before we go make the conclusion that, oh no, none of these features are useful in our model, let's actually visualize how these features are related to one another. And in particular, we're going to look at the egg weight, egg length, egg breadth relationships with one another. So just look in these boxes here. Also, we could look at the correlation matrix, and I'm just interested, for example, in how egg weight and egg length are correlated, how egg weight and egg breadth are correlated. And let's see, let's also include egg length and egg breadth there. In these cases, we can see they're highly correlated with one another, right? Which makes sense because the egg breadth and egg length would be related to the egg weight and vice versa. But when you have highly correlated features like this, then you get parameter values that are no longer interpretable. Because what happens is having a change in one of them, it may not be possible to change one while holding the others constant. And so then this idea of like, oh, this is the actual impact from this particular parameter isn't really true, because that particular parameter is actually really dependent on the others. And this is actually called collinearity in your features. If you have a feature that can be predicted pretty accurately by a linear function of the others, for example, if it's highly correlated with the others, then your slope values are going to be hard to interpret. It also means you are not going to have a unique solution for your parameters. So you can rerun that model starting at a different starting point for your numerical optimization, and you may get totally different slope values. Also, small changes in the data sample. So if you give it slightly different data, you're going to have big changes in your estimated slopes. And this idea of collinearity, or sometimes called multicollinearity, is what's happening in our example data set. Then it's suggesting you want to simplify your model. You don't need to use two features. If they're both collinear, then you could use one of the two, right? So, and in fact, if all three of them are collinear or multi-collinearity, then you could use one of the three. And so let's just pull out egg weight. And in that case, if we create this simple linear regression model, we get just as good of a model. I mean, our RMSE is basically the same. Our new RMSE is 0.0464. The old one, when we had all three in there, was 0.0454. So we basically have comparable RMSEs, but now our confidence interval for this parameter doesn't contain 0. And so now this is more interpretable. And again, this also aligns with our actual understanding. It makes sense that the weight of an egg predicts the weight of a newly hatched chick. So in general, if you have highly correlated features, it's going to prevent you from interpreting how the variables are related to the prediction, unless you remove some of the features that are correlated. Visually, what's happening here, you can think of this. If we had two features, if I have x1 and x2 that are correlated, you can imagine that there's some relationship between the two of them, like x2 is equal to some, I don't know, I'll say 3x1 plus 4, right? I'm just putting some type of relationship between them. Then I can't interpret the coefficients in front of theta 1 or in front of x1 and x2, because those, thinking of them as a slope measuring the change in y per change in x, is assuming that all the other variables are held constant. So this whole idea of when we were using our example of predict or interpreting our coefficients, and we were saying if two cats have a 1-inch height difference and the same hours of sleep, then their estimated weight difference is A1. That's true as long as length and sleep are not related to each other. If length and sleep are related to one another, then this interpretation fails. So if a change in length always came with a change of sleep, I can't make that interpretation that we were making before. And in that case, if you want your model to be interpretable and to be able to understand or to be able to make inferences about your coefficients, and they are related, then just get rid of one of them or more until you don't have all of your confidence intervals containing 0. So I'm also going to add as a caveat to all of this that when you're making inferential claims, especially by trying to say like, oh, this confidence interval didn't contain 0, so this is a significant feature to include in the model, that assumes that the regression model holds to start, right? So that it assumes there is actually a linear relationship, or that the output can be predicted by some combination of your features, and those features uniquely determine y, up to some noise. Also, if the assumptions of the bootstrap don't hold, then the results of the bootstrap might not be valid. So just a lot of caveats when you are trying to use your model to make inferential claims.